Driving LEDs with a boost regulator, microchip technology. Welcome to this training module on microchips driving LEDs with a boost regulator. This training module introduces the MCP 1650, 1651, 52, and 53 boost controllers and their applications for driving LEDs. A boost regulator topology is used when the output voltage of the converter must be equal to or greater than the input voltage. A boost regulator is useful for driving a chain of LEDs connected in series. It is beneficial to drive multiple LEDs in series. This ensures that all LEDs receive the same amount of current and will have the same brightness level. Using a coupled inductor in the boost circuit reduces the switching voltage requirements of the MOSFET switch. The MCP 1650, 51, 52, and 53 are 750 kHz gated oscillator boost controllers packaged in 8 or 10-pin MSOP packages. Developed for higher power portable applications, the gated oscillator controller can deliver 5 watts of power to the load while consuming only 120 microamperes of quiescent current at no load. The MCP 1650, 51, 52, and 53 can operate over a wide input voltage range, from 2 volts to 5.5 volts, to accommodate multiple primary cell and single cell lithium-ion battery-powered applications, in addition to 2.8 volts, 3.3 volts, and 5-volt regulated input voltages. Additional features integrated on the family include peak input current limit, adjustable output voltage current, low battery detection for the MCP 1651 and MCP 1653, and power good indication on the MCP 1652 and MCP 1653. This family has an internal 750 kHz gated oscillator which makes the MCP 1650, 51, 52, and 53 ideal for space-limited designs. The high switching frequency minimizes the size of the external inductor and capacitor, saving board space and cost. The internal oscillator operates at 2 different duty cycles depending on the level of the input voltage. By changing duty cycle in this fashion, the peak input current is reduced at high input voltages, reducing output ripple voltage and electrical stress on powertrain components. When the input voltage is low, the duty cycle changes to a larger value in order to provide full power capability at a wide input voltage range. The output voltage regulation is accomplished by comparing the output voltage to a reference internal to the MCP 1650, 51, 52, and 53. Here are pin descriptions of the device. External gate drive, output, drives the external in-channel MOSFET on and off during boost operation. Input peak current is sensed on the current sense pin through the external current sense resistor. When the sensed current is converted to a voltage, the current sense threshold is typically 12 millivolts below Vn. If that threshold is exceeded, the pulse is terminated asynchronously. Connecting output voltage of the boost converter through an external resistor divider to the feedback pin is for voltage regulation. The nominal voltage that is compared to this input for pulse termination is 1.22 volts. The shutdown input is used to turn the boost converter on and off. For normal operation, tie this pin high or to Vn. To turn off the device, tie this pin to low or ground. The low battery input is used for the low battery comparator. When the voltage on this pin falls below the nominal 1.22 volts threshold setting, the low battery output open drain is active low. LBO is an active low open drain output capable of sinking 10 milliamps when the LBI pin is below the threshold voltage. Power good is an active high open drain output capable of sinking 10 milliamps when the FB input pin is 15% below its typical value or more than 15% above its typical value, indicating that the output voltage is out of regulation. Other pins include circuit ground and input voltage. The low battery detect feature can be used to determine when the LBI input voltage has fallen below a predetermined threshold. The low battery detect comparator continuously monitors the output on the LBI pin. When the voltage on the LBI pin is above the 1.22 volts plus 123 millivolts hysteresis, the LBO pin will be in high impedance state, or open drain. As the voltage on the LBI pin decreases and is lower than the 1.22 volts typical threshold, the LBO pin will transition to a low state and is capable of sinking up to 10 milliamps. The power good output feature monitors the divided down voltage feedback into the FB pin. When the output voltage falls more than 15% typical below the regulated set point, the power good output pin will transition from a high impedance state, or open drain, to a low state capable of sinking 10 milliamps. If the output voltage rises more than 15% above the regulated set point, the PG output pin will transition from high to low. When power is first applied to the MCP 1650, 51, 52, and 53, the internal reference initialization is controlled to slow down the startup of the boost output voltage. This is done to reduce high inrush current required from the source. High inrush currents can cause the voltage source to drop suddenly and trip the UVLO threshold, shutting down the converter prior to reaching its steady-state operation. The gated oscillator is self-latched to prevent double and sporadic pulsing. The reset into the latch is asynchronous and can terminate the pulse during the on time of the duty cycle. The reset can be accomplished by the feedback voltage comparator or the current limit comparator. The current sense input pin is used to sense the peak input current of the boost converter. This can be used to limit how high the peak inductor current can reach. The current sense feature is optional and can be bypassed by connecting the VN input pin to the CS input pin. Non-bootstrap applications are typically used when the output voltage is boosted to a voltage that is higher than the rated voltage of the MCP 1650, 51, 52, and 53. For non-bootstrap applications, the input voltage is connected to the boost inductor through the optional current sense resistor and the VN pin of the MCP 1650, 51, 52, and 53. For this type of application, the S-option devices, UVLO at 2.55 volts typical, should be used. The gated oscillator duty cycle will be dependent on the value of the voltage on VN. If VN is greater than 3.8 volts, the duty cycle will be 56%. If VN is less than 3.8 volts, the duty cycle will be 80%. Here is a battery-operated boost LED driver example using the MCP 1650. An advantage of the MCP 1650 in battery applications is the gated oscillator architecture, which provides 2 duty cycles, reducing high peak inductor current and output ripple voltages. Input voltages above 3.8 volts engage a 56% duty cycle and an 80% duty cycle when the input voltage drops below 3.8 volts, extending battery life in these applications. The MCP 1650 is configured in the conventional boost topology, and is capable of generating output voltages of over 100 volts. 9 to 13 volt systems easily adapt to smart driver circuit to drive high power LEDs using the MCP 1702, MCP 1652, and a PIC 10F202 microcontroller. The MCP 1702 directly connected to the 12 volt source generates a 5 volt bias supply capable of delivering 250 milliamps to the intelligent boost control circuit. The LEDs are powered by the source voltage boosted by the MCP 1652, minimizing the current requirements for the 5 volt power system. A PIC 10F202 adds intelligence to the circuit, providing a means for thermal protection, load open and short circuit protection, as well as the capability of a user interface to control dimming and other features. Low battery detect of the MCP 1652 enables the designer to determine a trip point for a low battery condition to make smart adjustments to the circuit function using the PIC 10F202. In many applications, the input voltage can vary above and below the regulated output voltage. A standard boost converter cannot be used when the output voltage is below the input voltage. However, the MCP 1650, 51, 52, and 53 can be used as a single-ended primary inductance converter, a CPIC converter. An inductor and an AC coupling capacitor are required to achieve this configuration as shown in the figure. The CPIC converter can be a very popular topology for driving high-power LEDs. For many LEDs, the forward voltage drop is approximately 3.6 volts, which is between the maximum and minimum voltage range of a single-cell lithium-ion battery, as well as 3 alkaline or nickel-metal batteries.